Good afternoon, everyone. I'm Ahmet, and today I will be presenting our data science capstone project titled Comparative Analysis of Forest Fire Detection Models using diverse datasets created with Hasan Mert. Our problem is wildfires are growing global concern threatening both the environment and public safety. Early detection systems plays a vital role in preventing large-scale destruction by enabling timely intervention. However, the effectiveness of existing fire detection models often depends on the datasets and environmental conditions they are applied to. This variability raises the need for a true comparison of models across diverse datasets to identify the most reliable approaches. To address this problem, we use three distinct datasets obtained from Kaggle, each presenting unique challenges. Our first dataset primarily focused on forest regions, but with significant cluster imbalance. Our second dataset is a larger dataset and including some non-forest images which introduces noise. And the third dataset balanced in terms of class distribution and includes diverse environmental conditions such as mountainous terrain. These datasets allowed us to test the adaptability and robustness of the models across various scenarios. We also thought that using both traditional and current hybrid artificial intelligence models to work on these datasets and decided on three models. These three models has BBM467, which is known for strong feature extraction but computational heavy and slower in training. Our second model is Exception, advanced architecture capable of handling complex images with accuracy but requires more computational power. Custom CNN is a more traditional network but is a lightweight and faster in training but may not generalize as well as on complex datasets. Let's examine the datasets we talked about more detail with visualizations. Our tree dataset contains two types of labels as fire and non-fire. They contain over 30,000 images and 50,000 of which are fire and 15,000 which are non-fire. There are no unlabeled or non-volume images, but we noticed that a few of the images are not an image format and we fixed that. Our dataset seems to be a good fit for our project due to the large amount of image samples it contains, as well as its labeling format and ease of use. We think that we have enough resources to process the identification of fire image and forest. When we examined the images in the dataset, we discovered that the images were in different sizes due to the source they were obtained from. Since images of different sizes cannot work properly in the dataset, they all need to be resized to a fixed size. Let's talk about some data pre-processing process. First of all, in order to run our models properly, we converted the fire and non-fire values to binary by applying one-hop encoding. In order for the models to work most effectively on the datasets and to be tested in the most flawless way after working, we divided our data into the given ratios for training, testing, and validation purposes. Also, we used some data augmentation techniques. We artificially changed our dataset using data augmentation techniques so that our model could work more properly. To achieve that, we used image data generator. Let's examine our models with more details. As I said before, we have three different models to work on, and let's examine them by detail. First of all, Exception. Exception is short for Extreme Inception, is an advanced architecture that uses stepwise separable convolutions. This design significantly reduces the computational cost while it maintains high accuracy by separating spatial and channel-wise processing. Like BBM467, Exception was pre-trained on ImageNet. For our study, we froze its base layers and fine-tuned the dense layers. Similarly, the BBM467 setup we will talk about after the slides. BBM467 is a deep learning architecture pre-trained on ImageNet datasets, as we discussed. It's known for its ability to extract detailed features due to its uniform convolutional block structure. In our study, we fine-tuned its dense layers for binary classification. We froze the convolutional layers to retain pre-trained weights and added custom dense layers for adaptation. This included a flattening layer followed by a dense layer with 128 neurons and ReLU activation, dropout regularization to prevent overfitting a final dense layer with a sigmoid application for classification, as you can read on the slides. Our last model, which is the traditional model, CNN, Custom Convolutional Neural Network. This model was designed from scratch with three convolutional layers. Each layer had progressively increasing filters, followed by a ReLU activation and max pooling to reduce dimensionality while retaining key features. After flattening the output, it used two fully connected layers with 128 and 64 neurons respectively, followed by a single neuron with a sigmoid activation for binary classification tasks. Let's look at how these models worked on different datasets and evaluate them. We basically have four different performance metrics as accuracy, precision, recall, and F1 score to create a more accurate performance evaluation. First, let's examine the CNN model and how did it performed on different datasets. In dataset 1, it achieved 95% accuracy with a test loss of 0.11. We can see that class imbalance affected predictions, particularly in the fire class, highlighting the need for data augmentation for class weighting. In dataset 2, our CNN model achieved 98.7 accuracy and a test loss of 0.04, which demonstrates a strong learning capacity on large and diverse datasets. In dataset 3, our model performed well with a 96.7 accuracy and a test loss of 0.1365 loss. We can comment that the balanced class distribution improved its ability to predict fire and non-fire classes consistently. Our exception model achieved 94 accuracy and 0.15 test loss with a high AUG of 97%, showing excellent class discrimination despite being affected by class imbalance. In our dataset 2, our exception model delivered 97.8 accuracy with a 0.06 test loss and an outstanding AUG of 99.72%, and it shows that exception model handled the dataset diversity effectively in dataset 2. As a reminder, dataset 2 was our largest data frame. In dataset 3, it excelled with the best performance overall as 98.21 accuracy and 0.06 loss, with a almost perfect AUG result. It demonstrated exceptional capability on balanced and diverse datasets. Our VGG16 model achieved 92 accuracy and 0.2 test loss on dataset 1. It shows that class imbalance and lower robustness compared to other models. In dataset 2, it could achieve to deliver 95.45% accuracy with a test loss of 0.12. It indicates that it indicates an acceptable performance, but it requires more fine-tuning and augmentation for improvement. In dataset 3, it showed its best performance with a 96% and 0.1 test loss. So we can say that our VGG16 model benefits best from the balanced dataset and similar conditions. Best dataset for model CNN, we saw that dataset 2 is best. For exception, dataset 3 is best. For the VGG16, dataset 3 works best as well. And we discussed why they achieve better performance on these datasets. As a result, dataset 3 is the most effective for model evaluation due to its imbalance and diversity. The exception model consistently outperformed the others, particularly in handling complex data structures and maintaining high discrimination between classes, which make exception our choice for forced fire image tasks. CNN, while not most accurate, is computationally efficient and a viable alternative for resource-constrained environments. Thank you for listening to me. Please check out our references for